Hello. So in this video, we are going to look at the MOS device as an amplifier, and just as we did the common emitter stage for the BJT, we'll start with the common source stage. So with the common source stage, the device topology looks something like this. And the input voltage goes to the gate, and the output is sensed at the drain. Alright, let's use a small signal model to get the gain of the device. So this is the gate and this is the input voltage, and between the gates we have large impedance, almost infinity. Then we have the source. Okay, but we must mention that the input impedance is no longer infinity if the input signal coming here has a very high frequency, because this is a capacitor with the capacitance of Cox multiplied by the area of the device. We already discussed that in the very early videos of MOS devices, so we just need to keep that at the back of our minds. So you have the source, which is grounded. Then between, depending on the VGS, the voltage between the gate and the source, we will have the device operating as a current source if we are in the saturation region, and we already discussed the conditions for saturation region. Okay, so we are going to put RD here. So you see RD goes from the drain, so this is the drain, and from the drain to an AC ground. So this is an AC ground because it's not changing in small signal analysis. The VDD remains constant, so any voltage source that's not changing is replaced with an AC ground. But because the Vin will be changing with respect to time, it's always easier to think of it as a microphone giving a sinusoidal, and once you become more comfortable, you can just think of other voltage or input signal. It could be input from a sensor or something else. Okay, so I'm going to draw the RD from the drain to the ground. And I'm sensing my output voltage from here. So the output voltage is taken at this point. That will be the positive with respect to the ground. And the current here should also be the transconductance of the device, depending on its bias conditions, times the VGS. But in this particular topology, we see that the input voltage with reference to the ground will be the same as VGS, because VGS is the controlling voltage that controls the value of the current ID. So I can just write this is equal to GM Vin, and our aim is to find the relationship between V out and Vin. So we look at the current here. Assuming there's an output voltage, then there should be a current flowing from this node to the ground through resistor RD, and that current would have a value V out over RD. At the same node, we have this current leaving now in regards to RG. So the KCL at this node says that the current leaving the branch should be the same. They should add up to 0 since they are all leaving the branch. So I have GM VGS plus V out over RD. and they should all be equal to 0. Instead of VGS, I just have to make this V in. Already explained that VGS would be the same as VG with respect to ground, V in with respect to ground. All I need to do is find V out over V in, and that's going to be, if I put V out on one side and I have V in, so we are going to get this moving to the other side became minus, and before I divided through by V in, that's how V in got here, and I have to multiply through by RD to get rid of RD on this side. So this confirms something that we are already aware of. We also know that if we do not ignore channel length modulation, then we need to put GMRD in parallel with RO of the MOS device. Then we are already aware that we couldn't have increased the gain beyond a certain limit. So once the gain, we couldn't have increased the gain by increasing RD beyond a certain limit. Once RD increases beyond a certain limit, then it's going to be constrained or limited by the value of RO. So the maximum gain we can get from the device is GMRO, which is called the intrinsic gain. And for modern MOS devices in integrated circuits, it's somewhere between 5 and 20, depending on the ratio of length to width, W over L. So that one thing we need to also mention. We could also attempt to increase the value of the gain by increasing GM. Now GM has different equations, so let's just look at this one, which says to Cox W over L. Just hope I got that right. Then we have ID. Okay, so from this equation we could see that GM could be increased by increasing ID. Now let's see what happens if I increase ID. All along we know that for the device to operate as an amplifier, it should be in the saturation region. And what is the condition for the saturation region? I have my gate voltage here. Okay, so this is my source and this is my drain. Now if the drain voltage is above the gate voltage, then that is fine. But if the drain voltage falls way below the gate voltage, so I have my gate voltage and my drain voltage falls below the gate voltage. So this is my VD and it comes. Now the VD and the gate voltage are the same potential. Will the device still be in saturation? Yes. But if it further falls, and so let me put in values here. So let's assume the VTH is giving us 0.4 volts. This depends on the wafer that the device is being fabricated on, and the drain voltage is 1.0 volt and the gate voltage is 0.8 volt. In this condition, is the device in saturation? Yes, because VD is greater than VG, so there's no need to check. Once this condition is met, the device is in saturation, and we can operate the device as an amplifier because it can behave as a voltage controlled current source. Now we are in somewhere around this region. This VD against ID. Okay, what if the drain voltage reduces? Now we are saying the drain voltage reduces. We remember from BJT that as an amplifier, our output voltage sensed from here is going to be equal to VDD minus RD times ID. So assuming we have our VDD on top, that's the supply voltage, and our RD right here before taking our output voltage. Now we know that once we increase RD in an attempt to get more gain, we stand the risk of reducing the output voltage as this increases. You can see from the mathematics, and the output voltage is also our VD. So this is limited. We cannot increase. As we increase this, the voltage across this will increase, and that's the drop across the resistor. And taking the drop to get the voltage at the node below, we might risk reducing from VDD, which is arbitrarily chosen, to 0.8 if 0.8 is the same as the VG. But what if I further increase RD? Then means I'm going to further reduce the value of VD, and the VD can go below VG, just that it cannot go below VG more than one threshold. So if the VTH is 0.8, then VD could be 0.7. So it's less by 0.1. That is fine. It could be 0.6, which means it's less than VG by 0.2, 0.5, 0.6 by 0.6. So now VD is 0.6 and VG is 0.8. So VD is less than VG, but the difference is just at the threshold, one threshold, and this is the edge of saturation and triode region. If VD further reduces, either by we increasing this to get more gain, then the device will collapse in the triode region. In the triode region, we cannot operate the device as an amplifier. So assuming I also tried increasing GM to get more gain, the same condition happens. That's if I decided to increase GM by increasing ID. But there's another way out. Taking the formula for GM, okay, now taking the formula, okay, so I want to be sure if I got this formula right, so let me just try and prove it again. I'm not so sure. So I have this formula coming from ID is equal to the saturation formula over LCOX. Ideally, I'm supposed to write these two together, but for some reason I always manage to put this in between them. VG minus VTH, okay, square, and we, to get a transconductance, we differentiate this. So we have COX, now I'm writing it first, W over L, okay, VG minus VTH as GM. Okay, so how do we arrive at this equation? By making this guy the subject and putting it inside this guy. So if I'm making the overdrive voltage the subject, then it's going to be ID 2. Okay, so the 2 should be there, divided by mu n omega over L Cox. Okay, and I square root everything. Okay, so that should be it. So now this is the Vg minus Vth, and once I replace this guy, with all of this, then I unfactorize this inside that, so it comes with a square, means this will cancel the square, and that should be 2id and all this, so 2id. Okay, so that means, sorry about that, so just wanted to be sure. So that is correct. So you know that we could increase GM by increasing ID, or, which will be bad, we know that from V out is equal to V out is VD, and we don't want the VD to drop into triode region. So VDD minus IDRD. So if I increase RD too much, the device might go into triode region, and if I increase ID too much, the device might also go into triode region. But 2 is a constant, I can't do anything about that, I just proved it. The mobility is also a constant, I can't touch it, and this is also something I can't touch. But what about this? Remember, we said with most devices the designer has control over this, so that means we could get more GM and more gain by not touching the ID. That's the beauty of using MOS devices, and that is interesting. Then we begin to wonder and begin to be more greedy and think, does that mean we could increase this to infinity? Obviously not. So the limitation is that if you increase this, there's also an intrinsic value of the transconductance, which is given by ID over 1.5 Vt. Okay, so I hope this is right. And the value of Vt is what we already know from MOS devices. Okay, so that is it, at least. So how could we increase the gain? We could look in the next video other ways we could try and increase the gain, but let's just give this one shot and say goodbye for now.